So here we are in part 4, finally. I swear this is the last part studying the S-38 receiver. You know, the S-38 receiver was every man's radio, really every boy's radio. Once you guys all went off to college or left the farm, Mom and Dad probably took the S-38 out of the closet at some point and put it in the yard sale, or maybe it was passed down to another budding amateur or shortwave listener. But these things were built en masse. Hundreds of thousands of these S-38 style receivers, all the way from 1946 up through, well, 1962. You know, the S-120 was a very, very popular receiver. So Hallicrafters went from the octal tube lineup all the way to the miniatures and played it out. I believe the last Hallicrafters receiver to use tubes, and I have this receiver, was 1966. So they got their money out of a simple All-American 5 style receiver pattern all through those years. A great use of a simple circuit to get the kids interested in ham radio and shortwave listening. Let's finish this off. Where are we now? I've been able to take the receiver from a really bad hum situation, 170 or 180 millivolts peak to peak of hum with the receiver in standby, or with the potentiometer all the way down. The hum is worse than if the potentiometer is all the way up, something backwards there. The addition of the isolation transformer in the original refurbishment done by the radio shop, it really didn't seem to do anything in the hum regard. Yes, it did protect the receiver and make it safe. The isolation transformer definitely did that, but it did not act to fix the hum problem. I've gone through the cord replacement, working with the hot switching rather than switching the neutral on the chassis, very important. And we've learned about the capacitor, that death capacitor that connects the chassis to the outer case. Really, if you only did those 3 things, replace the cord with a polarized cord, replace the death capacitor with a proper capacitor, and rewire the switch for positive or hot switching, that would be enough for most people. If you want to go as far as to put in fuses and the safety capacitors that we went through, that's all the better. Before I put the lid back on, though, I want to pull on the thread of hum a little bit further. I don't think we're there yet. I think we can get the hum even lower on this receiver. So there's 2 more areas we're going to investigate in terms of hum. The first one is the filament to heater isolation performance inside the tubes themselves. Let's look at the health of the tubes themselves and how that affects hum. And then let's look at the grounding in the receiver. How well are the components actually grounded to the chassis, and I'm talking about the internal chassis of the receiver. Let's look at those 2 things before we get into the isolation transformer, which will be the last part of this video. We're going to look at an external isolation transformer system, whether you should bring ground through the isolation transformer or leave the ground disconnected. And we're going to look at the internal isolation transformer idea and what orientation that transformer should be in for the least hum pickup. This is part 4 of the S-38A in this case, but really applicable to the S-38 series from start to finish.
Last seen in part 3, our S-38A had been made safe with a 3-wire cord and the isolation grommets replaced, some rewiring of the on-off switch, and the addition of fuses and safety capacitors, which form a line EMI filter. Hum was reduced from a very annoying 170 millivolts peak to peak to around 30 millivolts peak to peak. The original set work had been done by a radio shop, and he'd done a great job at the recap and the realignment. The set was working very well on all bands. It was stable and sensitive. The BFO worked very, very well. But before going further, I had to remove the now redundant chassis to case capacitor that he had installed in the shop. The safety caps take care of that function now.
The first thing I want to do is remove the capacitor that was put in up here. This is the original capacitor that bridges the chassis to the outer case. The guy used a 630 volt 0.22, which is a good choice. This is a plenty safe capacitor, lasts a long time. So a lot of people just stick with this and you're done. No safety capacitors. But I wanted to use the safety caps, so the safety caps are down here on the terminal strip. Now let's do the wiring. For the wiring to the switch and back, I decided to use a shielded 2-wire cable. It's pretty big and thick, but instead of having 2 wires going across the chassis and back with all that high voltage AC on it around the sensitive components, I'm using a shielded cable to run the power up and back from the switch. The ground side is open down here, and it's connected to ground right at the potentiometer. Remember, one of the potentiometer leads goes right to chassis ground. So now we have a shielded AC connection back to and from the switch. Of course, one side, the side that's coming from the cord, is the fused hot lead going out, and the red lead is the return from the switch going right to pin 2 of the 35Z5 tube. Neutral is now permanently connected to ground with this connection here. So that's it. That's all the modifications needed for safe powering of the set. Now, of course, we have checked the power supply. The power supply is in good shape. The brand new filter capacitors are working fine. The set has been recapped. We don't have any problems with leakage causing problems. Now, it has been said that the couplet can cause trouble, so we're not ready to go there yet, but if that couplet is the next thing on the list, I will replace that with discrete components, but we're not there yet. The next order of business is to determine if you have a heater cathode short in any of your critical tubes, starting with the 35Z5, going to the 50L6, and finally the 12SQ7 preamp. You want to be able to check all 3 of those tubes, and that means you need to do tube substitution. So I've pulled out 3 tubes. I've got one of each, 35Z5, 50L6, and a 12SQ7. So I started with the 35Z5, no change. I went to the 50L6, and I found that the 50L6 in the set was a little bit better than my used substitute. So I kept the original 50L6. It was a little bit quieter. But when I went to the 12SQ7, that's when the magic happened. When I put this new 12SQ7 in, the output hum went way down, especially in standby. So I thought, aha, bad tube. But then when I put the original tube back in, it was quiet as well. So I think we have another factor here. It's called grounding and tube socket contact. So I sprayed the contacts of the tube socket. So let's turn it on with just the sprayed socket. Okay, so now we're on the scope. Let's go into standby. I can already see that we're in better shape. We are on the 5 millivolts per division. So I can honestly say that we've got the standby hum down to maybe 6 millivolts peak to peak. That's quite an improvement over the original 170. And of course, in standby, we can turn up the volume control, and we can see that now the mess, it's not really pretty, but the mess increases with the volume control. That's the way it should be. Hum should increase with the volume control and not just be at maximum all the time. I like that we can kind of see what we're doing now. So when we're in receive,
says a lifetime of resentment. University.
so now when the volume's down, I'm not hearing any hum at all. It's sounding great with the volume all the way down. It's really quite amazing. The next order of business, I think, is to possibly look at all of the tube socket grounds. They're using rivets everywhere. I'm a proponent for actually soldering the rivets. That is, shining up the rivets and trying to put a little bit of solder on there to make sure you have a good ground on the chassis. I think we've got some of that going too. Okay, I'm going to put up the volume a little bit. I'm just going to wiggle the tube. See that? I'm just wiggling the tube. This is the hot 50 L6. If I can do that, that's a grounded tube. If I can do that and cause that much change, I shouldn't be able to do that. Let's work on the grounds next. Of course, rivets made assembly on the production line very easy. Remember, these were not kit receivers. They were built in a factory. That was one way they were able to do a transformerless design safely, was by making sure they were wired professionally. So you can see where I've touched the socket here, the solder, nice and shiny. That took a very big soldering pistol to be able to do that. All of the sockets have been well grounded now. And I've also picked up some of the other rivets, like this one over here that goes to the standby switch. Any place where you see a terminal strip that's being depended on for ground, or a socket that's being depended on for ground, you want to make sure that you get a good connection from that socket to the chassis, and that's going to make a big difference with hum. I've got it back together. This is the cord, no isolation transformer. Let me put it in standby. Let's see if we can hear the hum. Should be a lot less. It's really low.
Shot during the attack, they right now are...
Okay, in standby, it's very quiet. Not hearing any sign of hum. Now, if I turn the volume up, I can start to hear some hum. Here at maximum volume, I can hear hum. But down where I'm going to receive a signal,
by saying play WGAF.
there is no hum. So, big improvement on the receiver. This guy's ready to go. But it's not, because we're going to take it apart again, and we're going to reinstall the isolation transformer. Before I do that, I do want to fire it up with an external isolation transformer. Let's see how that sounds. Okay, this is with the external isolation transformer with the ground through. Volume down. Not bad at all.
Dive back in to what it's like to be a mom.
Next, we're going to cut the ground. Now I have the isolation transformer without the ground going through, and we'll try it at a certain level that you can hear. So I'm in standby, volume full, and now I'm just going to connect the ground temporarily. Likes it better with the ground connected. Not a big difference though, really.
They don't want you to tell them that there is a wall there. The difference.
11:05, it is partly cloudy and 58 degrees.
You really have to change the whole receiver. You'd probably have to install a mains type transformer that has both a filament winding and a high voltage winding. You would twist all of your leads to your individual filaments. You'd probably have a diode instead of the 35Z5 and an appropriate dropping resistor. And you'd probably want to beef up your capacitors a little bit. Now the receiver would be completely free of hum. It wouldn't really be detectable at all. That's a lot of work. Of course, people in Europe have to do this when they have a 230, 240 volt line. Sometimes they will rewire the receiver with an appropriate transformer, like a 369 transformer from Hammond. I do plan on doing a project at some point where we do convert a receiver over. and install a proper tube-type transformer in it instead of just an isolation transformer. But I did want to show you that it can be done if you want to do the extra work. We're going to be talking about the internal isolation transformer idea. Now, this is a way to make the radio safe without having an external isolation transformer, and you don't have to worry about rewiring your socket. This is safer because it truly isolates the radio from the line and the neutral. This already had one on it, so it's already cut out to have the transformer mounted this way. But we also found that in the earlier video that there was quite a bit of hum pickup. And it really makes sense because the transformer is in line with the output transformer. These could couple. And it was in line with the speaker voice coil, which is just over the top. So you had 3 different mutual coupling opportunities right on top of the chassis. So the first thing I'm going to do is I'm going to extend the input and the output through these grommets. So I'll have some wires sticking up here, and then I will attach it to the leads so we have a way to kind of move the transformer away with a little bit of freedom. We can also determine what to do with the ground wire that's on the frame of the transformer. So how to wire the transformer in line? On the line side over here with power coming in, we have our fuses, we have our safety caps. We also want to have our switch involved. So the switch, the safety caps, and the fuses are all on the primary side of the isolation transformer. So we're breaking the neutral connection. The neutral connection on this side is going to go to the primary. The neutral connection on the other side is going to go right to the inner chassis. So that's the secondary of the transformer. You're going to pin 2, which is the input of the rectifier, and you're going directly to the inner chassis. That's your secondary windings on your isolation transformer. That way, all of the protection devices are on the primary side of the transformer, thus protecting everything downstream. Okay, I've got the primary side wired in. This is coming from the fuses, switches, and so on. And the secondary side. I brought out chassis ground. Let's see where this guy belongs. Here we are looking at the speaker output. I have the isolation transformer hooked up to primary and secondary. Everything is working. Volume's up full. So let's move this isolation transformer around the other transformer without getting a shock. Okay, yeah, I can definitely couple into it, no problem, right? In line. Very nice. And if I go right angles, I can minimize it at certain angles. If I go down to the chassis, okay, it definitely increases. So attaching to the chassis alone makes it go up. Okay, can you see that go up when I get close to the chassis? Now when I go right angles, I can still couple right angles. Okay, I put a 0.01 microfarad capacitor across the speaker leads to get rid of that peach fuzz that was the local oscillator bleeding through. I think it's a 65 or 70 megahertz scope, so it picks up the local oscillator quite easily. Shows you how much these things radiate. We picked up a little bit. It's more than 5 millivolts peak to peak now. It's around 7 millivolts, maybe 6 millivolts. Here's the mu metal. I'm simply going to take the mu metal and put it between the 2 transformers. There. I've got the mu metal between the 2 transformers, and you can see that we've returned to around 5 millivolts peak to peak. So the mu metal does its job breaking up the magnetic field between the 2 transformers. It's just an unfortunate place that you have to put this transformer. There's no room anywhere else. And frankly, you wouldn't want to put it on the other side of the receiver around more sensitive circuits. If we wanted to use the mu metal, we would attach it to the deck and wrap it around probably the audio output transformer. Let's try that. So remember, without the isolation transformer, we had about 5 millivolts peak to peak of residual hum. And I have fashioned the mu metal into a little bonnet to go over the output transformer. So we know that there is still some coupling between the transformers, but it's pretty minor. So let's see what the mu metal bonnet does. So the mu metal bonnet brings it back down to where it should be, at least. So I'm going to put the mu metal bonnet in the radio, and you do that by peeling off this backing. It's like a stickum. So it's like a tape. So we can literally just stick it down to the chassis. I do have a drain wire. It takes solder beautifully, and this will be attached right to the chassis. Although that doesn't seem to make much difference. It's actually the material that breaks up the magnetic field. It's not grounding anything. At least for the video, it shows you what mu metal can do in breaking up magnetic fields. I'm using some closed foam material to improve the vibration situation with the speaker. Why people don't try this is baffling to me.
WWV, Fort Collins, Colorado, broadcasting on internationally allocated standard carrier frequencies of 2.5, 5, 10, 15, 20 megahertz, providing time of day.
So this is WWV on 20 megahertz, band 4. So this has the internal isolation transformer installed. I think of the 3 configurations, the cord with no isolation transformer probably comes in second. The cord with an external isolation transformer is the best, and the internal isolation transformer is the worst. I was not able to get rid of the residual hum with the isolation transformer inside, no matter what I tried. They're just too close. The output transformer, the isolation transformer, and the speaker voice coil are just too close. Now, did I improve it? Yes, I drastically improved the hum situation. It's barely noticeable now. But did I solve it? No, I did not. But I gave it a good try. Turn down CHU. I'm not going to go through the alignment of this receiver. Now remember, this receiver came already recapped and aligned, and the alignment was pretty good. I did, however, go through it, and I found that 2 of the bands need a little touch-up on the oscillator for the dial to be absolutely correct. But I really have no comment on the alignment. It went very, very smoothly. Of course, I have a modern signal generator. The signal generator, you simply hook up to the antenna terminals, you put in the 455 direct and just blast it. Usually about a minus 30 dBm signal will come through the IF, straight through the mixer. Basically, you tune to a strong sideband station, adjust the CW oscillator or the BFO until you get good lower sideband on one of the lower bands, and then go up to the highest band and you should get good upper sideband. I didn't go to the point of absolutely zeroing it. I just went for the best sound on the BFO. That said, it's very easy to overload this receiver, and I highly suggest the use of a 1K potentiometer. You attach the high side of the pot to the antenna, and the variable wiper side of the pot to the antenna input of the receiver. This makes an RF gain control for the receiver, and it really helps with sideband. It's not too bad on CW, but it does overload quite easily on sideband. There is no automatic gain control in the sideband mode. Again, the alignment of the mixer and oscillator, very straightforward, very simple with the trimmers. Once you're done, check your dial, not only with the generator, but go to some check targets like this CHU at 3.33 or 7.85. Do your WWVs at 10, 15, and 20 megahertz. And yes, this thing picks up WWV very nicely on 20 megahertz when the band is open. So don't worry about sensitivity. Probably the band is closed, or you don't have a very good antenna for the higher frequencies. There's no real trouble with this if you have a decent high-frequency antenna for band 4. So did you guys enjoy this 4-part series on the S-38, the Hallicrafters AC/DC series of All-American 5-based tube lineups that gave us shortwave listening and early or novice type ham operation with low cost. Let's define low cost. The years after, immediately after World War II, thousands of B-17s and other types of aircraft, they all were loaded with radio equipment. All of that equipment was torn out and was sent to surplus. There also was a lot of new old stock or brand new equipment that was coming out on surplus. So for 47 or 50 bucks, you could have a brand new BC-348 receiver. So how was Hallicrafters, who really dominated the 1930s with their beautiful receivers? You know, if you look at the movies, the serials, everybody's using a Hallicrafters, right? They were fantastic marketers of their equipment. How are they possibly going to compete post-war with all of this surplus equipment? During the war, a AC/DC morale radio, or really an entertainment radio, had been developed called the EC1 Echophone. Also, Scott, there were many different morale-type radios that were AC/DC line-operated type sets. That was kind of the germ of this idea. An AC/DC set doesn't have a transformer, and of course it uses the standard All-American 5 lineup, so it's going to be lower cost. This is going to be a nice receiver that you can compete against the surplus gear. So the original price on the receiver was $47 or $49. So it was commensurate with the surplus receivers that hit the market. What does that amount of money represent? You can't talk about it in dollars. You have to talk about it in value. Think of it as your dad's salary for maybe a week of work, or maybe what you collected over a summer of work mowing lawns or delivering papers. That's the kind of value that a receiver had like this. It took a while to get that much value to be able to afford this receiver, but it was within reach, and that was what was important. They have some warts, right? Even though the front panel we know was designed by Raymond Loewy, who was the premier Art Deco designer of the 30s. He did, you know, the TWA logo and all of the oil company logos. He did, you know, the International Harvester tractor designs, the Studebaker. He's the one that did Air Force One layout and the blue and white color scheme. That's him. Well, anyway, he was the one that did the front panel, and we get these cool swept dials on the front of the S-38. So it looks cool to have this receiver on your desk as a 12-year-old in 1950. But it does have some warts, right? We know that the receiver has a hum issue, right? Because they're bringing the AC cord right up to a high-value audio gain pod, a potentiometer of 2 meg value, and an AC line cord do not go together very well. There's going to be some hum pickup. So the way they solved that was by putting ground or neutral right up at the control and switching the neutral lead. Well, of course, if you switch to the neutral lead, that's a dangerous situation. So that's one thing we had to fix with this series. We had to switch the hot. But now, how do you get rid of the hum? And then we shielded that line and got some of it back. So we had 3 methods, right? We had the proper 3-wire cord and doing the switching correctly, adding fuses, safety caps, other things like that to make the set safe. This is all after a recap, by the way. You want to get the recap done first. Then we worked on the external isolation transformer made with 2 transformers back to back. That turned out to be the least hum of all, by the way. And then finally, we took an isolation transformer, a 35-watt unit, and we put it inside the receiver. So that was a very difficult one to solve, and I ultimately think I failed, although the hum is much, much less than when I got the receiver. So what's this little box up here? This is the RF gain control, the poor man's RF gain control. It's just a 1K pot in a box. You hook the antenna up here, you take the phono connector back to the antenna and ground terminals, and this gives you a handy front-end attenuator for the receiver, just like the expensive receivers have. Hope you've enjoyed this 4-part series on the Hallicrafters S-38.